Hello, everyone, and welcome back to Flying Through the Gyroplane Flying Handbook. In this video, we're going to talk about the fourth chapter, which is technically chapter 18, and it's all about gyroplane systems. So let's go ahead and delve into this topic. So the first thing that is discussed is propulsion systems. And they do mention that the earlier gyros tended to have a tractor configuration, which is what most airplanes have today. And that later people switched to a pusher configuration, which is pretty much all you're going to see today in a modern gyroplane. They also started out using certified aircraft engines, and some of the home builds have moved away from that. Things like a little Benson gyroplane. You might see an automotive engine, the RAFs. Typically, you'll see a Subaru engine in those. But many of the modern gyros seem to like the Rotax engines, which are certified in some applications. Perfectly good engines. I would not hesitate to fly behind or in front of one of those. And then they get into the rotor systems. And there are different kinds of rotor systems out there. The most common that you're going to find for a gyroplane would be a semi-rigid rotor system, typically a two-bladed system. And why? Well, there's a couple of reasons. Number one, they're pretty simple. So what does a semi-rigid rotor system entail? It entails two blades that are allowed to teeter, and the teetering is necessary to account for that asymmetry of lift that we've talked about previously. So here is a rotor head from a semi-rigid system. You can see there's a teeter bolt, and that is the pivot point for the rotor. We also have our hub bar, and as we pointed out in a previous video, that typically is not going to be a flat bar. It's going to have a bend for a pre-coning angle. In other words, the amount of typical coning will be built into the bar, and that allows it to relieve stress on the blades. We don't really have anything else going on other than tilting the particular rotor head. We don't have any feathering. We can't change the pitch on most rotor systems. And then, of course, if you want to fly a light sport aircraft in the United States, you can only fly a two-bladed semi-rigid system that does not change its pitch. Anything else, and it becomes not a light sport aircraft in this country. And it looks kind of like this. Now, in the text, they talk a little bit about the fact that this is underslung, and why do you want it to be underslung? What does that even mean? So notice that this hinge, this teetering bolt, is above the plane of the rotor system. And why do you want that? Well, for that, I'm going to kind of haul out the Helicopter Flying Handbook, the current edition, and we want to talk about this. So here they're talking about an underslung system, and why do we want that? The reason we want that is very simple. If you think back to the figure skater that brings their arms in, as they bring their arms in, they accelerate. So if I don't undersling my rotor as the rotor tilts up and down, one side will have its CG for that side coming in, and the other one might be going out. And if you work out the physics or geometry, that will tell you that if you undersling it and you put this pivot point not in the plane but above it, now when this guy goes up, the center of gravity stays in the same horizontal position as this one does when it goes down. And that's why we have underslung systems. It reduces the stress. We don't have to have things like lead lag hinges, for example, in that system. They also discuss fully articulated rotor systems, not something you're going to see in modern gyroplanes for a couple reasons. Number one, not a light sport. Number two, more complicated, more expensive. So you're not likely to see that, but it is a possibility. So here's an example of a fully articulated system, and you can see that it has things like lead lag hinges that account for that force that we were just talking about and why we have underslung systems. We typically have a pre-rotator. Old school gyro, some of the times you actually pre-rotated manually by reaching up and spinning the disc. The higher you can get those RPMs before you start moving, the shorter your takeoff run is going to be, which is why the jump takeoff machines will pre-rotate to some crazy high RPM and zero pitch, around 500 RPMs in some cases, and then suddenly change the pitch, and the machine will literally jump off the ground. So when it comes to pre-rotators, we have a couple of different options. Here we can see a mechanical pre-rotator where it is going to engage this bendix on this gear. It's kind of like a starter gear that you might find in a typical engine. And then it's going to rotate your main rotors. So that's an option. We also have hydraulic pre-rotators. And what happens there, you're going to use the engine to drive a hydraulic pump, and it's going to do something very similar. Here we have the engine driving a hydraulic pump, and then that pump is used in order to engage this bendix and also spin that little motor. Other options we have electric pre-rotators. That's pretty simple. If you have electric, you just apply the power and the thing rotates, and you really could essentially use a starter to do that. And there were a couple other sort of interesting choices, things like tip jets. So you have jetted air at the ends of your rotors, or a jet engine actually. And this has a couple of advantages. You can pre-rotate pretty high. Also, it doesn't provide any torque back to the machine. It's not going to give you that typical torque where, you're turning it usually counterclockwise as viewed from above, and that makes the machine want to go clockwise. Well, none of that happens if the force is applied solely on the blades, and it's not supplied by a shaft from the machine, although it is rather loud to do something like that. And they talk a little bit about instrumentation. You can get away with very little on the instrumentation front. If you look at some of these old machines, they don't have much. They might just have the minimum required by the regulations, the good old tomato flames kind of stuff that they'll have. Engine instruments, part of that tomato flames, you might have coolant temperatures, cylinder head temperatures, oil pressure, possibly carburetor air temperature, exhaust gas temperature gauges. Again, those latter two are not required by any kind of regulation, so you may or may not have that. Most gyros will have a rotor tack. However, not all of them do. Some of the old Bensons, for example, wouldn't have a rotor tack. You just go until the thing took off and you hoped it was good enough. If you don't have a rotor tack in most modern gyros, that means the machine cannot be flown. And we'll talk more about that in the next chapter when we talk about the Rotorcraft Flying Handbook and how that relates to flying a gyro. So here's an example of a rotor tack found in a gyro. Again, some manufacturers require you to have this, some of them do not. And in the end, there's not a lot that you can do about your rotor speed. Your rotor speed is gravity fed. So the heavier you are, typically the higher your rotor RPM is going to be. You might have a slip skid indicator. Typically, this is just a piece of yarn attached to the windscreen often, and it works opposite from a ball in a turn coordinator. So in a turn coordinator, the rule is you step on the ball. If you have a piece of yarn, the rule is you drag the yarn. Airspeed indicator, again, typically this is something you're going to want to have. If it's an actual machine, not an ultralight, then you will need an airspeed indicator to be legal. And of course, you can have all kinds of airspeed indicators, from those that are just basically a vane to something you might find on an ultralight to a typical airspeed indicator as you would find in an airplane or a helicopter. Altimeter, you probably want to know how high above the ground you are. So you'll often find an altimeter. IFR in a gyroplane, there really isn't such a thing. There is no rating for flying IFR in a gyroplane. Now, however, if you want to get a commercial license to fly a gyroplane, you actually need some instrument flight time, either in a gyro or in a simulator. What about ground handling? A couple of ways that you can go with that. Typically, you're going to have a steerable nose wheel. There are some aircraft in the world that have a castering nose wheel, but the steerable nose wheel is by far more common, especially for a gyroplane. A lot of the gyroplanes don't have differential braking, and that would be the other option to control the thing on the ground. For example, all the autogyros, they have a finger brake that activates both brakes. So that's not a thing to have a castering nose wheel in those aircraft. And of course, brakes. And the brakes are going to help us to slow the machine down. So here's a quick look at a Cavalon rotor head. I'm just sitting here on the ground, and you'll notice as I push forward, it tilts that rotor head forward. It pulls back on my cyclic, it goes back. If I go to the side, it goes to the side. And I push the other side, and it goes that way. So you'll notice that the rotor is just very slowly spinning, and it's also teetering a little bit just because of the wind that I have here today. We can also see how the steerable nose wheel works. If I push on the pedals, you'll notice them move in the cockpit. And you notice that it also turns the nose wheel just a little bit. By the way, the Cavalon is not known for being able to turn very sharply. So if you have a 75-foot wide runway, that's about all that you're going to need just to turn the thing around. Here we have the Benson with everything proudly on display because it's just kind of open. You can see we have a standard pusher configuration for the engine. Also, once again, we have the teetering semi-rigid rotor system. And it is slightly underslung. If I look at my pedals, you do notice they slightly change the nose gear as well. If I were to try to pre-rotate on this machine, you'll notice the pre-rotator, it's got this little shaft and a Bendix. And let's see if we can see how that works. like so. So that's pretty much the gyro systems. So that's all for this video. We'll see you in the next one.